Hey folks, welcome back. In this video, I want to tell you about Green's theorem, which will be sort of a culmination of what we've been doing with vector fields. So here are some of the goals for this video. And let's pause to take inventory for what we're dealing with when we have vector fields. So in particular, we've only really looked at vector fields over two-dimensional space, over R2. And at this point, we can put them into two boxes, two categories. We've got path-independent vector fields and path-dependent. Remember, path-independent means that if you take 2 points in the vector field, it doesn't matter how you get from the first to the second, the line integral of that vector field is going to be the same. So it's independent of the path you choose. We saw that being path-independent is equivalent to saying that every circulation integral is 0. Remember, circulation integrals just are line integrals along a closed path, like a loop. We also saw, related to the fundamental theorem of calculus for line integrals, that conservative vector fields are path-independent. And in fact, this goes both ways. Remember, conservative means that it has a potential function, or that it's the gradient of some other function. So Green's theorem will give us a third category. We can add to this list a third equivalence to path independence. So the first thing I'll define for you is the notion of scalar curl. If we've got a vector field whose components are f1 and f2, and f1 and f2 both can be functions of x and y, then the scalar curl is a quantity we get by taking a partial of the second component with respect to x minus partial of the first component with respect to y. And now you might recognize these pieces as terms that we looked at when we applied Clairaut's theorem to a vector field to see if it could have a potential function. And that's right. So what does this measure? Well, before I tell you that, let's apply an example. Let's look at this vector field f, which is y squared x, and find its scalar curl. We'll take the partial with respect to x of the second component. We'll subtract from that the partial with respect to y of the first component, and we get 1 minus 2y. And I'll tell you that this quantity, 1 minus 2y, measures for us the rotation of the vector field around a point. That is, if we were to drop a twig or a paddle wheel into this vector field, say it represented the velocity of a flow of a current, how it would spin, or if it would spin. In particular, would it spin clockwise, in which case the scalar curl would be negative, or counterclockwise, in which case the scalar curl would be positive. So let's look at this point. I'll draw in blue here, 1/2 minus 1/2. And hopefully you can see that the vector field around this point would cause a counterclockwise rotation. You can see the way it's shaped. We can see that the arrows below it that are pointing to the right are longer than the arrows above it that are pointing up. And in fact, we can compute the scalar curl at that point. We know the scalar curl anywhere is 1 minus 2y. Well, at this point, y is equal to minus 1/2. So plug it in, and we get 2. At the moment, I'm not too concerned with the size of the scalar curl, but if it's positive, that's telling us there's a counterclockwise rotation. Let's try another point. I'll draw this one in green at minus 1/2, 1. And I think you'll agree that here the vector field, the velocity of the flow, would cause a clockwise rotation, in which case we should expect a negative scalar curl. And sure enough, if you plug in the y value of 1 into our expression of the scalar curl, we get minus 1. So you could try some other points. You can see that At any point where y is equal to a half, the scalar curl should be 0. So take a look, see if you agree with that. And then we'll look at Green's theorem. Well, actually, before I can tell you about Green's theorem, we need a couple more definitions. So the first will be that of a simple closed curve. To say a curve is simple means that it doesn't cross itself, and to say it's closed means it starts and ends at the same place. So here are some examples that illustrate that. And the next is that of an oriented boundary. So when we talk about the boundary, we're talking about a region in the plane. And the boundary is basically the curve that encapsulates it. When we say oriented, we specifically mean traveling counterclockwise around the region. So here are two examples. One yes, one no. And specifically, if the curve C is the boundary of R, we might use this notation to denote that. Note that as long as we've got a boundary without any holes, as long as we have a region without any holes, its boundary will always be a simple closed curve. Think about why that's true. So we've got all we need. In the next video, I'll tell you what Green's theorem says, and we'll look at some applications.